Welcome back to the Foundry by Forge College. Let's dive right in. Today, in our Advanced Solana Concepts track, we are figuring out exactly how to slice and route data efficiently across the network, without everything bursting into digital flames. If you caught our previous explainer on the principles of data sharding, you've already got the basics of mapping data ranges down. But today, we're moving from theory to practice. We're going to analyze concrete data sharding strategies and see how they actually impact network speed and scalability. So grab your virtual hard hats, because we are going full engineering mode today.
All right, here is our blueprint for this explainer. 1. Slicing data and fragmentation strategies. 2. Finding paths and routing trade-offs. 3. A real-world 100-megabyte scenario. 4. Simulating shard transfer times. And 5. Our conclusion and next steps. Okay, Section 1, Slicing data. Fragmentation strategies. When you're dealing with parallel transfer systems, think Solana's turbine, you've got a massive decision to make right out of the gate. It basically boils down to this. Do you ship a massive digital payload in one giant, heavy crate, or thousands of tiny, lightweight envelopes?
So how exactly do we chop up our data without creating an absolute nightmare for the receiving end? Because look, whatever you slice up, some poor node on the other side has to perfectly reassemble. The fragmentation pattern you go with directly impacts your transfer latency, your routing complexity, and, crucially, your ability to recover if some of those packets just vanish into the digital ether.
Well, we basically have 4 main fragmentation strategies to choose from. First up, fixed-size chunking. This is where every shard is exactly n bytes. It's awesome for high-throughput transfers across multiple paths, but if those chunks are too small, your header overhead just skyrockets. Second, we've got content-defined boundaries. This means cutting net semantic markers, perfect for files where you really don't want to split up logical units. Third is range-based boundaries. This uses predefined byte ranges, meaning smaller routing tables, which is totally ideal for large, contiguous data blocks. And finally, coded stripes, which actually use erasure codes to build in some much-needed redundancy.
Now, what's truly fascinating here is this concept of erasure-coded striping. I know, it sounds super technical, right? But it's honestly just like tearing up a treasure map and printing extra overlapping pieces. If one piece accidentally falls in the ocean, or in our case, a packet drops over a lossy network link, no worries, you can still find the gold. You can literally reconstruct the missing shards from the parity shards without ever having to ask the sender to retransmit. Sure, it costs a little bit more in CPU and encoding bandwidth, but for lossy paths, it's an absolute lifesaver.
Moving on to Section 2, Finding paths, routing trade-offs. Okay, so our data is perfectly boxed up, but now we have to actually route it through the network's chaotic shipping lanes. And how you size and label those boxes completely dictates how the post office is going to handle them. This brings us to a major trade-off. On one side, we have hash-based routing. You might use something like a SHA-256 hash of a block index to create a shard ID. This is fantastic for uniform load distribution, keeps things fair, but it does require high route counts and dynamic path selection. On the flip side, we have range-based routing. This lets you route contiguous ranges down the exact same path. The pro, your route tables are way smaller and simpler. The con, and it's a big one, it makes the network highly sensitive to traffic hotspots. Imagine if everyone wants the exact same contiguous range of data. You're going to get a massive digital traffic jam.
All right. Section 3, the 100-megabyte real-world scenario. Let's see how these mechanics actually clash out in the wild. Imagine you need to transfer a 100-megabyte state snapshot across a cluster. Let's say your per-link bandwidth is 100 megabits per second. Your median round-trip time is 20 milliseconds, and you have exactly 8 parallel transfer streams at your disposal. How do you slice up those 100 megabytes?
If we plug this into a performance model, we can test 3 different layouts. First, a large shard layout using just 2 50-megabyte shards. Second, a medium shard layout with 10 10-megabyte shards. And third, a fine-grained layout bursting with 1,100 kilobyte shards. Looking at these results, wow, the large shards take a sluggish 40.2 seconds. Why? Well, with only 2 shards, you're only utilizing 2 of your 8 available parallel streams. You're severely bottlenecking your concurrency. But check out the medium and fine-grained layouts. They absolutely fly, finishing in about 12 seconds, because they're fully saturating all 8 of those parallel paths.
But hold your horses. Don't go celebrating that 11.8-second time for the fine-grained layout just yet. To get that razor-thin speed advantage, you have to coordinate a staggering 1,000 separate shards. And remember, every single shard carries a fixed overhead cost. Header bytes, sequence metadata, checksums, plus every single one requires processing time in both the sender and the receiver. So the real takeaway here is that balance is key. Raw network speed arithmetic means absolutely nothing if your coordination costs are just crushing your CPU. 1,000 shards means complex reassembly buffers, sky-high memory usage, and massive coordination delays while the receiver waits around for out-of-order packets. And this right here is exactly why that medium layout, the 10 megabyte shards, was actually the unsung hero of our test. It hits that perfect sweet spot between maximizing those parallel streams and keeping the processing overhead totally manageable.
Which brings us to Section 4, simulating shard transfer times. You don't just have to guess at this balance. Much like we emphasize in our broader learning programs at Forge College, we can actually use a simple Python simulator to estimate these metrics mathematically way before we ever deploy code to the live network. The logic of our simulator basically follows 4 clear steps. Step 1, we estimate a single shard's delivery time. We do this by adding the round-trip time, the processing overhead, and the raw data transfer time. Step 2, we calculate the total number of shards by dividing our payload by our chosen shard size. Step 3, we divide that workload evenly across our available parallel streams. And finally, Step 4, we tack on a coordination delay that scales up based on the total shard count. This realistically models that messy reassembly overhead.
And here are the exact variables you'll need to feed into that model by plugging in real-world numbers, things like your total bytes, bandwidth, round-trip time, per shard processing overhead, header bytes, and your available concurrency streams. You get hard, actionable data. You can mathematically prove exactly why a specific shard size, like our 10 megabyte hero from earlier, hits the perfect equilibrium for your specific network profile. It completely replaces guesswork with evidence-driven engineering.
All right, Section 5, Conclusion and Next Steps. Let's roll up these engineering blueprints and synthesize the main mental models you need to take away from this explainer today. Because frankly, truly understanding these mechanics is what separates just a good network architecture from a genuinely great one.
Always keep in mind your ultimate lever in data transfer design, shard size. Smaller shards are going to maximize your parallel shipping lanes, but they will exponentially multiply your header and CPU overhead. Meanwhile, larger shards save you a massive amount of time on packaging and processing, but they bottleneck your parallelism, and you risk stalling the entire delivery if just one massive crate gets stuck on a slow path. It's a constant balancing act between CPU constraints and network constraints.
So here is a final thought to leave you with today. We spend so much of our time optimizing smart contracts, right? But ultimately, Web3's scalability is bound by the inescapable physical reality of moving data through cables. Are you optimizing your protocols for the realities of the physical layer? Think about it. Anyway, be sure to visit forge.college to explore more Web3 resources, dive deeper into these concepts, and join our community. Thanks so much for learning with us today, and keep building.